So this is actually a UI for showing the hardware that's connected to Windows. This is called the device manager. And you can see that there are all sorts of devices that are connected to this machine. Like for example, you can see that there are two disk drives under the disk drive menu and so on. But if you come down to the bottom, we have like two test sample drivers. And one of them is actually a user mode driver. And so, and this driver does not really have a kernel mode component. In fact, if you look at the task manager, this process, the WDF host, is the one that's actually running the driver. So, in fact, I want to see if I can end the process. I'm going to kill this process. This is actually the driver that's going to run. So I'm going to kill the process, and you can see that the driver went away. You can see that the driver got banned out. So that shows that. So this is essentially like I'm simulating a blue screen, right? So in the past, if you kill the driver, if there was a bug in the driver, and it took an exception, then you would get a blue. You would actually get a blue screen. And you had to reboot the machine. But now all you're seeing is the driver got killed, but I'm just seeing a red yellow bank. The device is not available, and the rest of the system is still available.
So you're really treating the driver as a process.
Yes,
in the
yes,
application.
just like any user mode process,
Fantastic.
any user mode application. And so,
You done with that?
Great.
yes.
Okay.
Okay.
That's very interesting.
Now, one question I have for you is, since you have this model, and it's basically you already have the proxy.
Right.
Let's assume we're on a 64-bit machine.
Right.
With, 12 gigs of RAM.
Right.
And what you could do in this case would wrap that in a managed wrapper and provide an API.
Right.
And so we'd be able to write managed code.
Right.
And it's still a kernel mode driver.
Right, right.
To us, the developer,
Right.
it's an
So
application.
actually, to be honest, even now you can do it.
Yeah.
So in fact, that user mode driver APIs are essentially COM. Well, they are actually very low-level COM. So we use COM for the interface definition. We use the abstract base classes. So we only, but we don't. You could theoretically if you provide sufficient layering, you could write this driver in VB, right? And but we don't expect you to do that. We expect you to write your driver in C++. Sure. But you could theoretically, even now, the interfaces are actually in IDL, right? They're COM IDLs, so interfaces. So you just you write your COM classes, and export those interfaces to the driver, and then to the framework, and then you can talk to it.
Fantastic.
So I also want to say that the model, one of the other cool things we're doing is to make sure that the driver model we are exposing in the kernel and user mode are similar. They use the same model. But yeah, one is in C, and the other one is in C++, right? Or COM, but they still have the same objects, methods, events, and properties, right? And so so the models are still the same. You still have a driver object, a device object, the queues. You have sequential queues and parallel queues. The methods are as similar as possible. The only interesting distinctions are that in the kernel mode, you get access to interrupts and hardware access, whereas in user mode, you don't have access to those kind of things. Mm-hmm. But if you are talking to a USB device, you really don't need that, and you can use our USB stack to talk to the hardware.
Sure.
The other, so you are talking about is writing in kernel mode really better for performance? Mm-hmm. So the answer there is kernel mode by itself does not give a performance improvement. In fact, there is a misconception that if you write code in the kernel, it improves performance. Mm-hmm. That's really not true. In fact, if you have a thread running in user mode and a thread running in kernel mode, they run at the same priority. It's not like when a thread enters kernel mode, we boost its priority. And they run at exactly the same priority. Okay. In fact, and a thread running in kernel mode could be context switched out and to a thread running in user mode if there's a higher priority thread. Mm. So there is no distinction. Okay. The only benefit you will get in kernel mode is that you can talk to other components directly because you're in the same address space. Mm. But so long as you are not talking to other components, then there's no real performance improvement. The other thing is that you don't have this context switch if you have a driver in kernel mode. But then the trade-off is that because of the context switch, you get isolation. So, I mean, the ability to actually recover from the failure. So the trade-off is one of performance versus isolation. And I would say that, for a majority of the drivers, right, that trade-off is worth it. Yes, there are some drivers for which performance is really key. Like if you have a gigabit network driver, you really want like every ounce of CPU you can get. So you probably want it to be in kernel mode. But for many other drivers, you probably don't need it.
Fantastic. Now, what about for video drivers?
So as I said, remember the exceptions I mentioned a while back, like which drivers cannot be moved to user mode.
Yes.
So one other thing is display or graphics. That is like one class where your performance is very high. And the other interesting thing is, if you look at display drivers, they don't do traditional I/O as much as something specific to their device class. So if you look at traditional I/O, you have bytes, some buffers in the application spice, you transfer it to the hardware, and then you get it back, right? I mean, you write out, you read or write data. With graphics, there is something interesting. So you have you are really probably sending it commands, asking it to render something in some piece of memory, and so it's really an additional processor. So while it is a driver, right? Yes, you need to talk to the other graphics core processor, and you have to probably do something with it. It's really another processor. It's really a multi-processor system, if you look at it that way. So in fact, that's one of the problems. Graphics traditionally has never been a. If you look at any operating system, graphics has always been the side, a special I/O, a special driver. It had all these weird special APIs and all these kind of things, right?
Sure. Now, we had talked with Neil Christensen's team, who are designing the new filter manager.
File system filter manager.
File system. Right. And you actually have done a fair amount of that work as well, working with Neil.
Yes, exactly, yes.
So a filter manager basically just rests on top of.
So I can show you where
Sure.
it. So if you look at this diagram. So if you look at the IO manager component, so the IO manager is really part of the NT kernel, and in fact, this exposes the APIs for reading and writing files and all that. So you have create file, will essentially call into the IO manager. So
Sure.
that's the interface. So in fact, you have the memory manager and so on. So if you look at then below this, you have a stack of drivers, right? So in his case, you have the file system, which is a driver. NTFS is a driver.
Okay.
And then on top of this, you have filters, file system filters, which essentially trap requests that are flowing down from the IO manager to the file system.
Absolutely.
So in the past, people used to write independent drivers. So this used to be like, antivirus vendor driver 1, and there should be another driver called antivirus driver 2, and so on.
Okay.
And the problem there was the NT-IO architecture says that you can tear the whole stack down, but you cannot take, when IO is in flight, you cannot take in one driver out, because you don't, when an IO is in flight, the architecture does not allow you to tear the stack down because IOs could be in flight. So you might be calling from one driver to another and boom, the driver goes away. That's not like a good thing.
Okay.
So what Neil's team, File System Filter Manager team does is they replaced one of the antivirus drivers essentially by writing what is called a File System Filter Manager. And this driver is always on the stack. So from the IO system's perspective, it's always on the stack.
Okay.
And then you write many mini filters,
Yeah.
right? And these are the ones that actually do the work. So now, because this guy is always on the stack, if this driver wants to be unloaded, it could be unloaded separately from this. It could be unloaded without disrupting the IO system.
Sure.
So that's how it works.
Fantastic. Yeah, I mean, it's a great model.
Right.
Now, is there any possibility of abstracting any part of that out into user mode, or would that be just insane? Performance.
I don't know if it is insane. That's an interesting point. I don't know if it's insane. Nothing is insane, actually. The question is, which parts should you really take and put it in user mode, right? As I said, performance is the trade-off. So this is an area where there's high amount of traffic, right? So every time somebody does read or write to a file, you have to go through this code.
I see.
And so, but then if you look at a mini filter, it may not be interested in read and write paths. It may be only interested in some specific path where it needs to check something, right? So you could imagine having a file-system filter manager that talks to a user mode driver and only redirects that and nothing else, right? And so for the rest of the path, it could still be in the kernel. So there are ways of designing this such that it works. I wouldn't rule it out, but this is something we are exploring. So one of the things, long-term goals is also to be able to isolate kernel mode drivers or sandbox them. So as I said, one way to sandbox them is to move them out of the kernel, right?
Sure.
The user mode way of writing drivers is one way. But then if there are drivers which we cannot move, then we need to try to come up with ways to sandbox them. And sandboxing is a new project. We are trying to figure out what are the ways to sandbox it. And so this is where if you could figure a way to put like some sort of a type-safe language and verifiable code in the kernel, you could probably get the sandboxing, right?
Sure.
But we don't have the, we are still doing prototypes, so I can't say
Sure,
we
that's
have
fine.
any value in it.
Sure, but the fact that you're exploring it is incredibly interesting.
Right.
And there certainly is no reason to believe that the CLR won't get more performant.
Right.
Code that's generated, the GIFs won't get better. There's no reason to believe that things aren't going to evolve in such a way that it will then someday make sense. And
That's
as you
possible,
said,
but think about this also. One does not really need the whole CLR and the runtime to work in the kernel. All you need is a type-safe language, right, and a framework, right?
Sure.
So in fact, the services you need in the kernel are not exactly the services you need in user mode, right?
Great
You really
point.
don't need all the namespaces and stuff that you have in user mode because you're not going to write such things in kernel mode.
Absolutely.
So what we are trying to do is figure out if you can take the language, right, and the IL and all those kind of things, and seeing if we can actually, come up with a runtime that actually can work in kernel mode and provide the type safety. Right?
Fantastic. So sort of like a KLR,
yes,
kernel language
Yeah,
runtime,
right.
where you support MC managed C++.
Yes.
Would be a good language.
Yes, exactly.
And you have a very small working set,
Right.
but you'd still have the GC, and you'd write your own
Yes, we
GC.
probably will need a GC because
Sure.
the type safe languages.
Then
yes,
it's totally
exactly.
verifiable.
Right.
But would there be something like a JIT, that kind of concept as well, or everything would be NGen?
I don't know about that. Jitting is actually dangerous because you can always, when you jit something at any time, it's a potential for failure,
Sure.
right? And so if you're on the paging file path and, I want to jit this page code for read because, I'm going to execute this code, and if they fail, that doesn't
There
help.
goes the system.
There goes the system. So you really don't want that. So you most likely probably want to, engine it before you do it.
Very interesting. Well, that's a whole very interesting topic in and of
Right.
itself.
Right, yes.
Because I used CLR because that's when I think of managed code. That's what I think about these days.
Right.
But there's no reason why there can only be one. That's an excellent point.
Right.
Depends on what job's trying to be done.
Exactly.
The fact is that verifiable code
Right.
is a good thing.
Right. Exactly.
Anywhere.
Right. So speaking of verifying, we are also my team also has like tools for driver developers who can which are static. So they are like you've probably heard of prefast, right?
Absolutely.
So we have a version of prefast for drivers,
Wow.
and we got another cool technology from Microsoft Research called the static driver verifier. Okay. In fact, tomorrow there's a talk at the architecture talks. So what this tool does is it essentially goes through your source code and finds bugs. Right? Prefast does it too. Prefast looks at within the scope of a function, whereas static driver verifier, you can actually look at the scope of an entire program and essentially enforce rules. So in the past, we had this tool called the driver verifier, which will essentially validate at runtime anytime. So if you turn on the driver verifier on a driver, every time the driver calls into some function, it'll actually validate that the driver is indeed following the rules correctly.
Sure.
So for example, if you're actually acquiring a spin lock, if you're acquiring a spin lock at interrupt level, right? That's a rule that you cannot acquire the spin lock. That's a problem. So if you call that, the verifier will say, you're acquiring a spin lock here. It's a problem. Bug check, right? Or it'll say, okay, this is a problem, and then the developer can actually can fix the bug. But if it's static driver verifier, you run this tool just like a lint or something, right? You run it on your source code, and it'll actually say, this is the interrupt subroutine. You are acquiring a spin lock here, error, right? And you can fix the code right there, right?
Fantastic.
So that's like one of the things we are trying to do. that's actually pretty interesting technology because it's actually analyzing a source code as an NP. I mean, it's actually you cannot. It is there are a lot of abstractions you have to do. You can never terminate potentially, right? So
Sure.
there is a very cool technology called SLAM that was developed by our Microsoft Research, and we are using that to improve the quality of drivers.
That's fantastic. And that's just
In
great.
fact, you can find a lot of these things on the web. So you can. So if you want to look at some of the work I'm doing, you can
Sure.
actually look at Microsoft.com. WAC WHDC, WAC WDF,
Okay.
and you can find the prefast, static driver verifier, and all that. And you can also find some of the other rules and regulations for driver developers and all
Fantastic.
that. So
Great. Well, thank you so very much. This has been very enlightening. It's glad to hear there's so much work going on in this level that's going to improve stability, etc.
Right.
One question I do have:
Mhm.
when you move stuff out from when you're proxying into kernel mode from user mode,
Mhm.
you still are dealing with the security model of the kernel.
Yes, right. So one of the things when you do that, when you think about the user mode framework architecture, we have to think a lot about security because, well, in kernel mode, drivers are completely trusted. They are in kernel mode.
Mhm.
So in user mode, we still want to trust the driver to talk to its hardware because clearly only it knows how to talk to the hardware. Otherwise, we wouldn't have a driver in the first place,
Sure.
right? So we need to give it sufficient security to talk to its hardware. But one thing we can do is prevent that driver from accessing things it should never access in the first place. Like for example, if you're in the kernel mode, you could do you can actually access anything, right? You can probably access the some very critical piece of system information. Whereas in user mode, you could actually bound it and prevent it from. You can only talk to each device and nothing else, right?
Excellent.
So those kind of things, yes, we are definitely thinking about.
Cool, and that's actually a huge win.
Right.
Moving them up into user
Right.
mode, get more control.
Better security and better control.
Yeah.
Absolutely.
But of course, there is a security manager in the
Right.
kernel, and we should probably talk to those people too, huh?
Right. So in fact, the IO manager is essentially implementing the security for IO subsystem, right? So it is talking to the security manager to validate it, and so we will be. When you talk to a user mode driver, you'll still go through the same security manager, right? So you'll implement. You can have ACLs on your devices and everything, and in fact, that's one of the beauties of this architecture,
Sure.
is that the security model remains the same, and you can essentially apply the same rules, and any innovations in that space will still apply to this one. right?
Fantastic.
So,
So in other words, it's an example of a super cool new feature where you don't lose any
Right.
security.
right.
Excellent. Great. Well, thank you so much.